In the previous section, we saw what it meant for a relation to be reflexive, symmetric, and transitive. If a relation happens to have all three of those properties, we call it an equivalence relation. And that's because, well, the equals relation is all three of those properties, and there are other relations that have all those three, and they sort of act like an equality of sorts. One really important one is the equivalence mod k relation, or congruence mod k, and you can see on pages 455 and 456 why those are equivalence relations. Okay, so it turns out that partitions actually give us a way to define equivalence relations. So recall the definition of partition from a previous chapter. The point is, if you're given a partition of a set, you can define from it an equivalence relation. Well, I'm just saying relation at the moment, but we'll prove later that it ends up being an equivalence relation. So remember that a partition of a set is a separation of that set into however many pieces. The pieces may not overlap. None of the pieces may be the empty set, and they union up to the entire set. So for example, take the integers and split them into the evens and the odds. Then that's a partition. We've seen that before. Let's then use this definition to then define a relation on the integers, which is defined from the partition. So I usually write the partition as a set itself. It's a set that consists of the subsets that form the partition. So I've written out here the partition of the set Z into two sets, the evens and the odds. And from this, using the definition, we're going to go ahead and define a relation on the integers. So let's define the relation R to mean the following. It's going to mean, given two integers, n and m, we're going to say n r m and is related to m if and only if there's a member of the partition that both of those numbers is in. So either n and m are both in the even set or they're both in the odd set. So this relation that we've defined is precisely the same thing as, saying n and m have the same parity, or n and m are congruent mod 2. It's a familiar idea that we've seen before. But as we'll see later, defining this relation in this way actually makes R have the reflexive, symmetric, and transitive properties. In other words, R will end up being an equivalence relation. Okay, so you can do actually the same thing for any congruence mod k. So you can partition the integers up into pieces depending on their remainder, division mod k, and something similar happens. We'll actually look at that carefully later. All right, let's do a completely different example to get us practicing working with power sets. So I've just grabbed a set of size 3. Let's say A is the set of numbers 4, 7, and 20. And I want to define a partition on the power set of A, not on A itself, but the power set of A. So the partition is going to split the entire power set up, all the subsets of A, into different groups. And the grouping that I want to do is I want to group the subsets of A by their size. So the smallest subset of A has no elements. That's the empty set. There are some subsets of A that have size 1, the singleton sets. And then you have subsets of A of size 2 and just one subset of A of size 3. So I'm basically going to put those subsets into 4 different camps. Okay, so the first member of the partition just consists of the empty set, because it's the only set that has 0 elements. And then the second member of the partition, again, each of my members of the partition is a subset of the power set of A. The second member of that partition is all the singletons. So it's got singleton 4, singleton 7, singleton 20. So that's a grouping of the subsets of A of size 1. And now I group together all the subsets of size 2, and finally I put the one subset of size 3 into its own partition member. So these sets right here, I'll label A1, A2 to keep with the convention. These are the members of the partition of the power set of A. They are subsets of the power set of A. It's hard once you get this many squiggles in one discussion, but to clarify a little bit, let me list out the elements of the power set of A one by one as a reminder, and you can see more clearly that Indeed, I am just grabbing these elements of the power set and putting them into baskets according to their size. Okay, and then, as the definition says, we can define a relation on the power set from this partition. So we're going to define a relation R on the power set of A to mean that given any two subsets of A, or any two elements of the power set, they're related to each other. So let's say B is related to C if there is a member of the partition that they are both inside. So that would mean that B has the same size as C. So just to work through a couple examples of subsets of A, singleton 4 is related to singleton 20 because they both have size 1 and they both are in the member A2. But singleton 4 is not related to 420 because they're not in the same partition member. Okay, so to summarize, given any partition of a set, you can define a relation from that partition in the manner that we did in the previous two examples. The next theorem argues that when you do that, the relation that you build ends up being an equivalence relation. So in order to prove that statement, I would have to prove that anytime you have a partition and you define a relation in that manner, then that relation has the symmetric, reflexive, and transitive properties. I'm just going to go ahead and prove one part of that, and I'll leave for you to read or prove on your own the other two parts. So what I want to do here is I want to suppose that A is a set and P, let's make it curly P, P is a partition, and let's say the partition consists of the sets A1, A2, A3, and so on. It doesn't necessarily have to be a finite partition. It could be infinite. And in fact, it gets kind of crazy when you talk about like higher cardinality situations. It doesn't even need to be the case that the partition sets are enumerable in any fashion. But let's just say that the partition we're dealing with looks like this: A1, A2, A3, and so on. So I've got some set A, and I'm splitting it up into however many pieces. Okay, so let's try and prove that, let me define the relation here. So let's define X, R, Y to mean that there is some AI in the partition such that X and Y are in AI. Okay, so the claim is, of course, that this relation ends up being an equivalence relation. Sorry about the sirens outside. Let me go ahead and prove for you that it is reflexive. Okay, so let me remind you what it takes for a relation to be reflexive. What it means is that for all X in the set, X needs to be related to itself. So maybe off to the side I'll write that. For all X in A, X are X. That's what I'm trying to prove. It's different than proving symmetric or transitive. Remember, those statements are conditional statements. This is just a straight up, I got to prove that, all right? So I'm going to go ahead and let X be in A. That first sentence in my proof is guided by the structure of the statement reflexive. And then I have to figure out why it would be the case that X is related to A. Well, what does it mean that X is related to A? It means that there is some AI in the partition such that X is in AI. Listing X twice here doesn't really say, it just says X is in AI. Okay, so why would it be the case that since P is a partition, why would there be some AI that X is inside? Well, let me scroll up to the definition of partition. I think I have it here somewhere. And we can figure that out. All right, here's the definition of partition. It says that if you have a set A, a finite or infinite collection of sets is a partition if two things hold. A is the union of all the AIs, and the AIs are mutually disjoint. So actually, I think it's this first condition that tells me what I want. Since A is the union of all of the AIs, the union, that means if I select any X in A, it must be in one of these AIs, because that's what it means for A to be the union. If X is in a union of something, it means it's in at least one of those things. So I think I've got my idea now. I'm going to come back to my proof and write that out. Okay, so I let x be an A, and I say since A is the union of all of these partition sets, A1, A2, A3, and so on, there is some I such that x is in AI, and this is literally the definition that x is related to itself. So x is related to itself. Hence, R is reflexive. Okay, so as I said before, it's a good practice to do the other two parts of the proof, show that the relation is symmetric, show that it's transitive. It's all written out in the book if you need help, but it's an important result.